All right, you're not going to believe this, but this is my third time going through this problem this morning. I went through it once, and I paused it 3 minutes in, and finished the problem, and went back and redid the whole thing. Here it is. This is what we're doing in just a second. Then I went and that didn't record, so I went back and did it again, and I ended up with this, which was 16 minutes of blank screen and no audio. So now we're going to do it again. This is the third time. So you guys better get it by the end of this, because I'm going to get it. Third time through. Would you flip over that example sheet to the back? And let's work through it. I hopefully don't lose my mind. So I went through and I erased the work I had done to get it prepped. Now you'll notice in this one that I actually made a chart for myself, and I think that you should push pause and make this chart right now. Now we're not going to solve for the temperature, pressure, and volume at each point. We're just going to jump right in. So I made a chart for delta U, Q, and work. Push pause, catch up, and go. So first thing I notice when I look at the graph is that my pressure axis is in times 10 to the 5th pascals, and my volume axis is in liters. Now, I need to remember that there are 1,000 liters in 1 meter cubed. Therefore, 8 liters is going to be 8 times 10 to the minus 3 meters cubed. Or I could write it as 0.0080 meters cubed, just to be reminded. Okay, so without further ado, how about we tackle it? What do you say? So to fill it in this process, I see from the graph that we're starting off at point A, and it's going to go through 4 different processes before it returns back to A. So it's going to go from A to B. Now, what type of process would you call that? What's not changing based on the graph? Yeah, that's right, Maggie. The volume is not changing. Therefore, that would be an isometric process. How about from B to C? B to C, what's not changing? Yeah, good, Brady. Yeah, nice. It's going to be isobaric. And it's going to be isobaric expansion because the volume is getting greater. C to D is going to be isometric again. And from C to D, I can tell the temperature drops because in my mind, I can sort of see some isotherms. And D would definitely have a lower temperature than C. See, I can see that. And then from D to A, the gas would be compressed isobarically. Okay, so I think the key to solving these is to start off with stuff I know I can calculate. And one thing I know I can calculate will be the change in internal energy, because I can find the internal energy at each one of these positions. So the internal energy at A is going to be 3/2 PV. I could solve it up in terms of temperature, but I don't need to because I have pressure and volume given on the graph. So that's going to be 3/2 times a pressure of 1.5 times 10 to the 5th times a volume of 8 times 10 to the minus 3. When I plug that all in, I'm going to end up with, you think by now I would know for certain what it was since this is the third time through, 1,800 joules. Good. So I'm going to take that and fill it in right here. Oh, wait, no, I'm not. That's just that. That's not the change in. That's just what the internal energy is at that point. So I'm going to push pause. Hopefully it keeps recording after that this time. And you are going to find the internal energy right now at B, C, and D. Ready, go. All right, it's recording, hopefully. So here it is. I filled, I calculated U, A, B, C, and D easily enough. And then to find the change in the internal energy, I just need to find the difference. And I voted out because I get nervous about the signs. As the song tells us, it's all about the signs. So I'm going to have 4,800 joules at B. At A, it was 1,800 joules. So the change in the internal energy from A to B is going to be 3,000 joules. Yeah? Are you good with that? Of course you are. It's too easy. Now, from B to C, it also increased. So I take the 12,000 minus 4,800, and I get that the change in internal energy increased 7,200 joules. Now, from C to D, it decreased. I just realized I made a typo right there. That was going to be 4,500 joules. Now, it decreased. D is 4,500 minus the 12,000. So we end up with a negative 7,500. What does that mean? That means that heat flowed out during that process. And from D to A, what do you end up with? Yeah, negative 1,700 joules. I think I'm going to double check that because I do not feel like repeating this whole thing again. Oh, it's negative 2,000. Really? Huh. Negative 2,700 joules. Okay. Now, let's go back up to the graph. Here's what I see. During process AB, it's isometric. Can you find the area under that curve? No, you can't, because it's a vertical line. There is no area. No work was done on or by the gas because the piston wasn't increasing in volume or decreasing. It wasn't being compressed or expanded. So the work is zero. Same thing is true for C to D. Check, check. That's easy. Now, using our first law of thermodynamics, we should be able to find the heat during process AB very easily. Yes, I know the answer is 3,000, Josh. Shh. That's the third time I've had to stop you today. Just kidding. You're not there. But, and this is my first time through with you guys now. Find the heat during AB. So I got delta U equals Q plus W. So since the change in internal energy is plus 3,000 and the work was zero. Yeah, Josh, you were right. It's 3,000 joules. That means 3,000 joules of heat must have added to the system as we went from process A to B. Now, from C to D, there was no work done, but the internal energy decreased. So heat had to have flowed out of the system. Flowed. It flowed out of the system. And what is this stuff that comes out of the tailpipe called? Oh, yeah, exhaust. The system would have exhausted that heat. 7,500 joules. Okay, let's keep going. Now, when I look at process BC, I see that it's an isobaric process. So I can find the area under the curve. Now, the area under that curve goes all the way down to the bottom, and I can find that work done by doing W equals negative P delta V. So let's do that. Let's do that for process BC. So work equals negative P delta V. The pressure was 4 times 10 to the 5th. And the change in volume, I've got to do final volume. So 20 times 10 to the minus 3 minus 8 times 10 to the minus 3 And the work done during that process, that's right, it's going to be negative 4,800 joules. Right? Yeah. So that means that work done by the gas was negative because the gas expanded. Think of it, it like pushed down against something and applied a force over a distance, and it did work. But the gas itself didn't have work done on it. It would take away from the internal energy of the gas. So to find the heat added during that system, during that process, I can say that delta U for B to C is Q plus work, right? And if I have positive 7,200 equals Q minus 4,800, I think this is why I show it this way, so that you don't mess up the sign. You know what I end up with? 12,000 joules of heat had to have been added during that process. Okay? So heat was added and the gas expanded. Now, if I play the same game with D to A, I can find the area under the curve from D to A, and that would be the work done on the gas. Why don't I do that? Let's do it. So to find the work from D to A, work equals negative P delta V. That pressure times the change in volume. The change in volume is going to be I'm running out of room here, 0.08 minus 0.20. Right, I just converted to meters cubed there. I got the work done is positive 1,800 joules. So work done is positive 1,800 joules on the gas. That makes sense because like something compressed the gas, and as it compressed it, it did work on it. During that process, though, heat must have flowed out. If I do delta U for dA is Q plus W, and if we have negative 2,700 equals Q plus 1,800, that means the heat that flowed out is going to be negative 4,500 joules. Okay. All right. So as the gas was compressed, heat had to flow out. And back up. Think about it. Work was done on the gas to compress it, but somehow the temperature still decreased. That can only happen if some of the heat was exhausted out of the system. Okay. So let's add it all together. Let's add it up. So for the entire process, what was the change in internal energy for the entire thing? Add them all up. What do you get? Yeah, that's right. You get 0. And that should make perfect sense because you're right back where you started. Just like me, doing this video 3 times today. God, this better be the last one. Now, for heat, take that column, add it all together. What do you get? You know what you get? You get plus 3,000 joules. Because in reality, what happened is that you added 15,000 joules of heat to the system. But along the way, you exhausted 12,000 joules of heat. Wasted heat, wasted energy. But the total net heat added to the system would be 3,000 joules. If we look at work, the work done for the system would be negative 3,000 joules. That means that essentially what you've done is you've taken 3,000 joules of heat and you've converted that into 3,000 joules of work. We took heat, but we turned it into work. Now, some of you are thinking, wow, that's like 100% efficient. How can that work? No. We added 15,000 joules of heat, and we only got 3,000 joules of work out of it. So really, the efficiency would just be the work divided by the total heat added, or 3,000 divided by 15,000, or 0.2, or 20%. So this is not very efficient. We'll do more with efficiency later. Last thing I'll mention before I close this up and pray that it works. If we look at our graph, you can see that we colored in yellow all the way down to the bottom. Then we colored in the green. And what I have here in the middle is what I would say is the net work done on the gas. So the enclosed area of any PV diagram is going to be the net work. Like those are two separate words, net work. Done either on the gas or by the gas. That part depends. Okay, I hope I didn't miss too much the third time through. If so, I'm not doing this again. I hope you guys are okay. Take care of yourselves, and tomorrow we'll do more problems and start to see how this all really ties together.